Hello. This is week six in my journey to become a machine learning engineer, and in this week we looked at the theme was CNNs, convolution neural networks. We particularly looked at you only look once algorithm or model architecture, which really pushed the state of the art in object detection, specifically real time object detection, due to how quickly this algorithm can be applied, especially during the inference phase. So basically, that our task was to apply the YOLO architecture or algorithm to identify and detect multiple digits in an image. So as you know, if you have one image and you're trying to guess what that number is, that's a very easy task. However, detecting where the image is and detecting the boundary boxes is a more complex task, and specifically when also we have multiple digits in an image. So that was our task. We basically had, I would say, 4 days, because as a one day is dedicated for research. So Wednesdays are dedicated for reading state of the art research in computer vision in CNNs. So really, we had 4 days to get the data set in the right format, to build the model architecture, the loss function, everything, do all the coding, and actually have the end-to-end part of it, which means our model should be able to work on a server where it receives a request, which someone draws an image on a canvas. We receive that and we send back, first of all, identifying the numbers, what numbers are on the canvas, but also drawing a boundary box around each one of them. So lots to do, and I'm going to walk you through how the week went on basically. First of all, we all went and read the article to understand what YOLO is, and basically what the YOLO algorithm does, it divides an image into a grid, and then for each grid we try to do many things. The first one is, um, each grid will try to guess, is there an object within it. So that's what we would say confidence. So for example, one grid would say, I'm 70% sure there's a dog um, in the pixel or in my boundaries. Then it would actually also predict the bounding box, and so each grid will say, I think the bounding box for this entire object is as such. And then it also would say how sure the grid is that this object belongs to a certain class. So, for example, in this image, we might have two classes: image in dog and bicycle, and car, maybe like three classes, and each pixel will say, I'm also 80% sure that in the bounding box I predicted there's a dog, or the other one would say a bicycle, and associate a probability to each of the three classes. So that's in a nutshell what YOLO is. But basically, also in terms of the architecture, it's the one that you can see here. It's a typical convolution neural network, with fully connected at the layer, max pooling layer. Yeah, it's really typical. And as you know, we have to go from one phase to the other. We have the filters; they sweep across the image and extract or reduce the features um, into a smaller size, but it increases in depth, as you can see. So you can see that we started with a 448 by 448 by 3 channels, but then by doing a convolution and then a max pointing layer afterwards, it went down to 120, 112, and 112, but the depth went from 3 to 192. So you can see that this progresses as we go down the channel. And then finally we get to the fully connected layer, as you can see here, where it's all flattened into 4096. And then finally we go back um, to like a 7 by 7 by 30 layer. And what this means is that each one of these 7 by 7 blocks is a grid cell that is making a prediction on the following: how confident is there's an object in it or around it, what are the boundaries of this object, and finally which class it belongs to. And actually, it there's a in some algorithms, you can also each grid can predict multiple bounding boxes, um, and then at the end, we would choose the one with the that the pixel or the grid cell is most confident about. So it might say, you might ask your algorithm, each grid cell I wanted to predict 5 bounding boxes. So like each grid cell will go and create 5 bounding boxes, and at the end you'd ask your model, okay, which one are you most confident that the object detected is in it, and you would choose one out of these 5. That's another level of complexity. The loss function is quite complex, as you can see. There's a multiple elements to it. The first element that you can see here on top, these are the coordinates of the bounding box. So obviously you want to minimize that as much as possible so that your prediction coincides, or the center of the box the predicted center of the box coincide with the ground truth center of the box. The second one, we're still talking about the bounding box, but this time we're talking about the width and height. So again, you want to minimize that. You want the predicted height and the predicted width of the bounding box to be as close as possible to the ground truth. The third and the fourth element, there are two of them for a reason. Both of them are talking about the confidence of having an object inside the grid cell. So as you remember, each grid cell says, I'm this much confident that there's an object. Um, yeah, there's an object in the bounding box I'm predicting. But as you know, there will be a lot of grid cells or a lot of bounding boxes where there won't be any objects in them. So, if you have a well, an image and you're actually going after one or two objects, there's one or two objects, there will be a lot of bounding cells that will have nothing in them. The thing is that if we leave it as such and we just, instead of having these two items here, we just have one, the loss due to uh, the bounding boxes with no object is going to eclipse or be very, very large compared to all the other losses. So that might create some stability issues. So for this reason, they were split into. For those where there's a prediction that there is a bounding box, so we have this loss function here. And for those that are saying there is no object, we multiply that by a lambda, which is usually very, very small. It's about zero point 0.5. And that's why the loss due to all these no object predictions is reduced, and its impact on the loss function is reduced, and that helps with stabilizing the algorithms or the gradient descent in calculating the loss. Right. Okay, so the way I've done that actually, when I was reading the article, I just felt there's a lot of levels of complexity, which means multiple grid cells, multiple bounding boxes. The loss function has different items. So I said, all right, let me start from the simplest method possible. And so I set a first milestone is I want to assume that my image has only one grid cell. So no multiple grid cells, just one. The entire image is just one grid cell. It will have one digit in it and one bounding box, and I will just use the data from the MNIST dataset on digits. That meant, that was actually quite straightforward. The loss function was quite easy to implement, and also I forgot to mention the labels would be 1 by 15, and the 15 is corresponds to the following. The first one is the confidence. How confident is my single grid cell that there's an object in it? So it will be one always in my first data set or first training process. Second, the four consecutive digits are the center, so the x coordinate, y coordinate of the center of the bounding box, and then the next two are the width and the height of the bounding box. So that's 5, and then the remaining 10 are the classes because we have 10 digits from 0 to 9. So in total, the label for each training record was 15 items. So I worked on that, got that to work, everything was fine, and this is okay. Now we're ready to move to the second milestone. Now let's split our image into 4 grid cells. So now we have 4 grid cells. Each grid cell is going to make a prediction for these 15 labels that we saw earlier. But now because we have 15, we have 4 grid cells. Now our label is 60. So basically for each record, we will have 60 predictions, but still here we're looking at a single digit with one bounding box. So one bounding box, forgot to mention that as well. Yeah, no, I did actually mention that. So one bounding box, no two or three bounding box. So right, there were here some changes to be done. First on the dataset, so the dataset has to be modified compared to the previous milestone. The loss function now had to be added, to include the loss due to the grid cells predicting no object in them, and so on and so forth. So I worked on that. Also got all the code running nice and clean, and the accuracy was going up. The loss function was going down. Everything seems to be okay. And then once I was happy with that, I was ready now to move to the next milestone. The next milestone was fine tuning. So basically, when I was testing, on the second milestone, when I started testing it, I trained it on one digit and I says, okay, now I want to see how it performs if I add multiple digits. And it was performing really bad. It wasn't doing any good. So, okay, now we need to add multiple digits. And what I did is the following. I added, you can see in this image that there are four. So now we have four digits in the image. But actually, what I was doing is I was randomly adding a certain number of images. So one image might have one, another image might have two digits, another image might have three digits, and some image will have four. And that was chosen randomly. So now my data set looked way different than before. Now I have four digit or a certain number of digits between 0 and 4, and for each one we have their own labels. So again, in total the label was 60, and this time it wasn't really well. What meant is that I had to go back and change the dataset code, because now I don't have a single digit. I have to randomly add a certain amount of digits in the image, and then once I was done with that, again I started fine tuning and seeing the accuracy go up, loss function go down again. One thing I noticed is that I stopped reaching the accuracy level I was reaching before. So before I was getting to like 98, 97, 97 or 97, 98% accuracy. The more I was adding digits, it was going down to 88, 89%. I didn't focus on increasing the accuracy there because I just wanted to get first my model up and running, and then I started working maybe on the model architecture, revisiting how many convnets, how many layers, etc. But first, I wanted to get all of that done. Okay, so I started training and I felt like, okay, I got 88% and the model actually stopped getting any better. So I said, okay, I will be happy with that now. And then I moved on to the next milestone. So the next milestone, as you can see in purple, is now the images are coming from Mnest and Thera. What is Thera? Thera is the platform that is going to send the requests. So basically, on Thera, a user will going to go on the platform and draw a number themselves with the mouse, and we will receive that canvas with one, two, or multiple images, and we will need to send back a prediction regarding what digits we are seeing in the canvas, but also a bounding box around each one of them. So what happened when I tested my model from the previous milestone is that it was working good on the Mnest dataset, but once it received the Thera, nothing. The predictions were quite bad, whether it was the bounding box or the actual digit. So okay, it seems that the model is not learning the digits from Thera. So what I did is I did a few about 10 or 15 images from Thera. And then I went back to my dataset and I started injecting these into the dataset while I was preparing the dataset. So what you can see, for example, here, what I was doing in the process is every training record has at least one image coming from the Thera dataset. So if I have one image, I would randomly choose between a Thera image and a Mnest image. If I have two digits, then one is going to be Mnest, the other one is potentially going to be a Thera or Mnest, and so on for the three or four digits. But basically, if I have four digits, they'll definitely be a Thera image. So then now, okay, now that I injected these Thera images into my dataset, I fine-tuned again, um, and I'll show you in the notebook some of the results that I got. So you can see here on my GitHub. If you go to the notebook, right, you can see here. So how large the dataset class has become. It's become really, really large. So I think a lot of the effort was concentrated here. One thing I would like to do better later is you can see there's a lot of if statements. It's filled with if statements, which I think was making my model quite slow to train. But I just had to, because we were moving really quickly, just have to with this approach. But I'd like to go through it again and make the code more efficient. Right, let's get back to our topic, which is looking at the output of the model on the test dataset first. So if you see on the test dataset, is this the test? Yeah, this is the test dataset, and it's doing really well. So here we have, this is the ground truth. We have 3919 with the corresponding bounding box, and this is now my prediction. 3919. It's doing pretty well. This is the 9 you can see here. This is the 9 coming from the Thera image. So you can see that it's doing way less better than, for example, the 9 coming from the MNIST. So that's something to be worked on. It's not doing well with images drawn by random users. It's doing pretty well on the MNIST data. So that's something we need more data from Thera, to be injected in the model so that the model actually learns to detect these numbers. Here's another example. So let's say 0093. This time my model predicted 0090, so it failed on the 3. But in terms of the bounding boxes, it looks pretty good actually. Let's have another example. This one is interesting because, as you can see, the 2 is a bit quite close to the 9. Let's see. So the ground truth is 8902 with these bounding boxes. My model predicted 8802, so it failed on the 9. When it says 0 here, it means it didn't find anything, not actual like a 0 digit. Um, but as you can see, the bounding box, again, not that great. So it failed to detect that the 2 was here. And I think there are two reasons. I believe this is another 2 that from Thera. But also, if you remember, I had split my data set in a grid of 4, and the tried to and positioned the images in each quadrant. So this one here, for some reason, seems to be quite in the middle. So the model is failed to detect the bounding box around it. So that's another thing the model is probably not learning, which is if the digit is not in one of the 4 quadrants, it doesn't know how to draw the bounding box around it. So that's something else that needs to be adjusted. Um, but yeah, I mean, overall, I think it's here 2049. So it's predicting. Oh, this was a great one actually. This is another example where the number 9 is actually, so this is a number 9 also coming from the Thera, but it did a better job than the one we saw earlier. So yeah, you can see that the model is, this one is a great one. This one I think is 100 over 100. So 0314, 0314, and the bounding boxes look pretty well. I mean, the 1 is a bit thin, but I think this is a great one. This is a great example. The 3 here, this is a really bad one. So that's a pretty bad example. 0900, 399, but the bounding box is pretty bad. 3, yeah. These ones done a good job on the bounding boxes, but it didn't guess the 5. It guessed it as in 9. So this is super interesting, I think, and that's, I would suppose, what I would be working on next. Let me also check because I think I did. That's a lot of images. Yeah, you see here, for example, so this is an image where all the digits are coming from Thera. As you can see, it's not doing that well. So first of all, in terms of digit prediction, it predicted 3902, so only got one right. The 4 and 6 were wrong, and also the bounding boxes aren't that great. So the model is not generalizing. When the data is coming 100% from Thera, it's doing pretty bad, and that's something I need to look into and probably need to generate more data and fine tune the model more on these hand-drawn images from the platform, from the Thera platform. So, but I think this is really cool. This is pretty exciting, and I really enjoyed this week. And I would say, if I think back on how much, like how do we distribute our time while working in our team, I would say 90% was on the data preparation and synthetic data set creation. So pretty much, the loss function, when we worked on the YOLO, the architecture was, quite simple. When you use PyTorch, you do a few convnets, max pooling layers, fully connected layer. That's pretty much it. That does the job really for the dataset we were working on. The loss function was a bit complicated, so we spent a bit of time coding that. But that was pretty much it. And the rest of the time was on the dataset. It's figuring out, and that's actually the biggest challenge I would say that we faced, is knowing what the model is failing to learn and having a data set, creating a data set that allows the model to learn these things. So, for example, like you can see on the left, when it was coming from the MNIST, the model was doing really well, whether it was detecting what digits they are, but also the bounding box was doing a fabulous job. But then when we got to the MNIST data that you can see on the right, these are, random users creating digits on Thera. It wasn't doing as well. Sometimes it was, not detecting the right digit, sometimes not detecting the right number, but also the size of a digit. So if you can see here to the top left, if I draw one big five across the entire canvas, the model actually was struggling to uh, to learn that. So there was a lot of gaps in the model's learning that we needed create a specific data set to create that. So I think that's one of the biggest learning I think in this week is how much it's important to have a data set right for what you're trying to predict in the outer world. Um, and second thing, which I would want to continue, is figuring out, like in a more methodical, scientific, quantitative way, what is the model not capturing? What is it failing to learn? And go back and see what we could do, whether it's reviewing the architecture, having more data, having better data, having different data, etc. That's something that I'd like to work on in the upcoming weeks as well. One thing I also wanted to share, which we did on Wednesday during that research day, is looking at the FCN, the fully convolution layers. So the CNNs, or even the YOLO, you could see that there's a fully connected layer right here where you have to flatten all your features into one row. That's called a fully connected layer. And due to that, the thing with the CNNs is you cannot have an arbitrary input size. Your input image always have to have the same size, which actually sometimes could degrade the quality of the image. So if you squish things, like if you have let's say you have a rectangular image, more on the width than on the length, and then your model actually only accepts square images, then you will have to squish your rectangle into a rectangle, which will change a lot the quality of the image and the shapes actually in. Um, so the what we read in that research article was about FCNs, fully convolutional layers. So you can see here that you only have convolutions. There are no fully connected layers anymore. What's good is that it can be trained end to end, which means, as I mentioned earlier, it can accept any input size. You don't need to do any pre-processing of squishing the image, resizing, etc. And also, it outputs an image as well. So again, you don't need to do any post-processing. It just spits out an image that you can immediately use in your work. And finally, it does a pixel to pixel prediction, which is called dense prediction, which means that it makes a prediction for each single pixel of the image. So previously, we would look, YOLO, you only look once. You would sweep the entire image and say, there's a dog and there's a cat, right? But you would make a prediction for the entire image. Now you make a prediction for each single pixel, and you say this pixel has this pixel has this, etc. And so the advantages of FCNs, as I mentioned earlier, that they can take input of arbitrary size, they make predictions per pixel, end-to-end training, and what's really good is that inference time is even further reduced. As you know, YOLO was pushing the state of the art in real-time object detection. FCNs reduce inference time even more. So that's super interesting, and that's something that I wanted to look at and see, potentially how that might impact the model results that I had. So another item that I would like to explore more are the FCNs. And yeah, that's pretty much it for me today. On Saturday, yeah, had a really good week. Um, it was another exciting one. Last week we fine-tuned Llama, which was super interesting and exciting. This week we're doing CNNs with computer vision, so we're really having a blast, and I cannot wait for the upcoming weeks. I think we might be doing stable diffusion, which I really hope we will. And probably the last week is going to be more about MLOps. So how we use different available tools when we really want to scale things. How we use Kubeflow to develop everything, but then also how does Kubeflow interact with Apache Kafka to get some real-time data? Then how does it speak to Hadoop as a database to have more processed offline data? And then how does Airflow, Apache Airflow, orchestrate all of that? Scheduling. How do we automate and schedule everything to have a pipeline that is working autonomously? So yeah, very exciting stuff. We still have 2 more weeks in our in that journey, and then the journey obviously doesn't end there, and then it will be up for us to take that and see what we can do with it with our own project, in our own companies, in our own teams. How can we take all this learning and start innovating and using machine learning in what we do? And the journey will continue even with MLX. It's an 18-month journey, really. So there will be continuous learning every week with the Machine Learning Institute team. Um, so yeah, thank you for watching, and see you next time. Bye.